Welcome to UBG Bytes. Today we're taking a deep dive into something really core to macOS security. It's called the Mandatory Access Control Framework, or, MACF for short.
Right.
And we're not just talking about those permission pop-ups you see all the time. This goes, well, much deeper. How macOS manages security fundamentally.
Exactly. It's the foundation.
Yeah.
And to really get into it, we've been looking at Apple's own security documentation, the Apple platform security stuff.
Okay.
Plus insights from folks like security researcher Jonathan Levin and also Census Labs. They've done some great work here.
Cool. So our mission really is to figure out how this MACF thing works and why it's so vital for protecting macOS overall.
Let's do it.
Okay, so first things first. Mandatory access control. What actually is that in simple terms?
Well, think of MAC, Mandatory Access Control, as a very strict security guard. It doesn't just check who you are, like your user account. It looks at special labels, security attributes, really.
Labels on what?
On both the thing trying to do something, like an app or a process, that's the subject, and on the thing it's trying to access a file, maybe some system resource, the object.
Oh, okay.
And access is only granted if the labels match up according to a central set of rules that are, well, mandatory.
So it's not based on my settings as the user necessarily?
Not primarily, no. That's the key difference from what most people are used to, which is discretionary access control, or DAC.
Right, DAC is like, I own this file, I decide who reads it.
Exactly. You, the owner, have discretion. With MACI, the system enforces the policy based on these labels, consistently, everywhere. Even administrators often can't just override it easily. It's much more rigid top-down.
Okay, that makes sense. So MACF then is Apple's specific implementation of this MAC idea within macOS. It's the framework doing the enforcing.
Precisely. MACF is the engine, the set of tools and mechanisms macOS uses to actually put these fine-grained, label-based security policies into action. It goes way beyond standard user permissions.
Got it. So how does this whole thing get started? When you boot up your Mac, our sources mentioned policy registration.
Yeah, so right near the beginning, when the macOS kernel is starting up, or when these little helper modules called kernel extensions, kexts, load up.
Like system plugins?
Kinda, yeah, low-level ones. Anyway, a specific function gets called, Mac Policy Register. Its job is basically to sign up different security modules, and these modules provide hooks.
Hooks, like checkpoints.
That's a good way to think about it.
Yeah.
They're predefined points in the operating system where MACF can jump in and check things. These hooks are defined in structures called Mac Policy Ops.
Okay.
And one really important function mentioned is hook policy in it. This is the one that actually loads the specific rulebooks, the security profiles or policies that MACF will use.
So boot time, register the security modules, load the rulebooks. Got it.
Pretty much. And a prime example of a security feature built using MACF and these policies is sandboxing, something you find on both macOS and iOS.
Ah, the sandbox. Yeah, we hear about that all the time for apps. That uses MACF.
Heavily. Sandboxing is basically MACF creating a very restricted environment for an application. It limits what files it can see, what network connections it can make, what system resources it can touch.
Right, it contains the app. So if an app gets compromised, it can't mess up the whole system.
Exactly. It's like putting each app in its own secure little playpen, enforced by MACF rules.
Now, the sources say the sandbox itself is closed source on both Mac and iOS, which I guess makes sense for security. But they're implemented differently.
Yeah, that's interesting. On macOS, while the core logic is closed, the actual file, sandbox.kext, that's the sandbox kernel extension, it has symbols.
Symbols?
They're like internal labels or names within the code. They make it, well, easier for researchers to figure out what different parts of the code do. Reverse engineering is still hard, but it helps.
Okay.
And also on the Mac, the actual sandbox rulebooks, the profiles, are stored as separate files. You can actually find them in System Library Sandbox Profiles.
And what are those files like?
They're written in a special language called Sandbox Profile Language, as BPL. It's based on a language called Scheme, apparently a simplified version.
Huh, okay. And no container.sb file, specifically.
Right. That specific file name isn't typically used in the standard macOS setup, unlike some other systems.
So that's the Mac side. What about iOS, iPhones, iPads?
iOS is, well, even more locked down. The sandbox profiles aren't separate files. They're compiled, sort of baked right into the sandbox.txt itself.
Oh, okay.
And that iOS sandbox.txt, it doesn't have those helpful symbols like the macOS version. Makes it much harder to analyze.
A real black box, then.
Pretty much.
Yeah.
Though, as the Census Labs folks found, there are still some readable text strings inside that can give clues, but it's definitely tougher going for researchers.
Okay, so same principle, MACF enforcing app isolation, but different implementation details, especially around how open the profiles are.
Exactly.
Now, let's dig into how MACF actually makes a decision. An app tries to do something. How does the check work? The sources talk about operations and callbacks.
Right. So any action an app attempts, like opening a file, connecting to a website, maybe accessing your contacts, that's considered an operation from MACF's perspective.
Okay.
MACF intercepts these attempts and checks them against the rules defined in those loaded security profiles we talked about.
And these operations, they have specific names or labels.
Yes, they correspond to what are called MACF callbacks. These are essentially predefined functions that the system knows about. You can find their definitions in a header file, security-macpolicy.h.
So, like a dictionary of possible actions.
Sort of, yeah. And the actual code that runs for each callback, the logic that says yes or no, based on the rules, the code lives inside the relevant security module, like the sandbox.txt.
Okay, so an app tries Operation X, MACF sees it, calls the callback function for X inside the sandbox text, which then checks the rules.
That's the basic flow, yes.
Right.
Let's take a concrete example from the sources. The IOKit get properties operation.
Okay, what's that?
That's about an app trying to get information, properties, about hardware devices connected via IOKit, like details about your graphics card or USB devices.
Right. So how does MACF handle that specific request?
There's a specific type definition, MPOYOKit check get property. It basically outlines the function that needs to check. Can this process, the subject, get this specific property from this specific IOKit device?
And where does that check actually happen in the system code?
Well, when some part of macOS needs to get a hardware property, it might call a function like iRegistry entry get property. And inside that function, it makes another call, macOS check get property.
Ah, okay. That's the MACF check itself.
Exactly. That function triggers the MACF mechanism to consult the active policies about this specific get property operation.
Our notes also mention something called the macOS check macro. How does that fit in?
Ah, yes. Mac check. That's crucial. When the system needs to perform one of these checks, like our macOS check get property, it often uses this Mac check macro.
And what does the macro do?
It's quite clever. It iterates, meaning it goes through the list of all the MSC policies that are currently registered and active on the system.
All of them, not just the sandbox.
Potentially all of them, yeah. For each active policy, it checks if that policy has implemented the specific callback function for the operation, being checked, in our example, a function matching the MPOYOKit check get property pattern.
Okay.
If a policy has implemented that function, MACF check calls it. So each relevant policy gets a chance to evaluate the operation and potentially deny it.
Wow, so multiple layers of policy could be checking the same action. That sounds robust.
It is. It allows for complex, layered security. And circling back, remember the hook policynet function we mentioned earlier?
Yeah, loading the policies at the start.
Right. Census Labs noted that when this function runs, it actually prints out the name and like a full identifier for each policy it loads, which is pretty handy for researchers trying to see what security rules are actually in effect.
Definitely helpful. Okay, so we understand how operations trigger checks against potentially multiple policies. Let's talk about the policies, the profiles themselves. How are they structured? How are they loaded?
So we know the callbacks check against loaded profiles. The research, particularly from Census Labs looking at the code, points to a function called profile create. This seems to be central to getting these profiles set up in memory.
Profile create, what does it need to work? What are its inputs?
It takes a few key things. XD is apparently a pointer to some memory space where the profile context gets built. X1 points to the location within the kernel extensions code where the raw packed profile data is stored.
Raw rules, okay.
Then X3 gives the size of that packed data, and X2 and X4 are flags, probably controlling options for how the profile is processed.
So it unpacks this raw data using these parameters. What's inside that packed data? What's the structure?
Based on the reverse engineering, it looks like this. There's a header first, then something identified as iOS version magic, maybe a compatibility check.
Makes sense.
Then, crucially, information about regular expressions, or regexes. It stores the location of an array of offsets pointing to the regexes, and the total count of regexes included.
Regular expressions, like pattern matching. in security profiles.
Here's like it, yeah. The data includes the offsets, the length, and the actual pattern strings for these rejexes. This allows for more flexible rules, like allow network access only to servers matching.apple.com or something.
Interesting. Okay, what else is in the packed structure?
There's a count of the actual profiles packed inside, and then this important structure called ops filter struct.
Ops filter struct. What does that do?
It seems to act like an index. It contains offsets or pointers that link specific operations like our IOKit get properties, or maybe file open to associated filters.
Filters.
Think of filters as the specific conditions or checks applied to an operation by a policy. This ops filter struct likely helps MACF quickly find the right set of filters to apply when a particular operation happens based on whatever policies are active.
Gotcha. So it's a way to efficiently connect an attempted action to the specific rule checks that need to run.
Exactly. It ties the operations to the conditions defined within the profiles.
Okay, let me try and summarize this whole thing then. MACF is this really foundational security layer in macOS, right?
Absolutely fundamental.
It works by having security policies register themselves, setting up checkpoints or hooks. When an app tries to do something, an operation MACF intercepts it.
Yep.
It then uses callbacks, specific functions tied to operations, to check against the loaded security profiles or rulebooks.
Perfect.
And sandboxing is like the most visible example of MACF in action, keeping apps contained using these rules.
Couldn't have said it better myself.
These profiles, while often closed source, especially on iOS, have this complex internal structure. They use things like pattern matching with regexes and these filters linked via the ops filter struct to enforce very specific controls.
That really captures the essence of it. It's complex, deeply embedded, and incredibly powerful.
It really is.
Yeah.
And thinking about how pervasive MACF is across macOS and iOS too, it makes you wonder, doesn't it?
Wonder what?
Well, how might future changes to MACF itself, enhancements or maybe even undiscovered vulnerabilities, how could that impact the security of basically all of Apple's platforms? It's such a critical piece.
That's a really potent thought. A change at that foundational level could have massive ripple effects, for better or for worse. Definitely something to keep an eye on.